Hello, friends. This is Michael Bohm with Youth Apologetics Training. Today we're going to keep going on this series about the Anthropic principle, just the whole concept of the universe being fine-tuned for life. There is a multitude of factors that have to be satisfied in order for life to exist anywhere in our universe. And so I'm going to start by reading some examples of some challenges that any life would have to overcome in order to live somewhere in the universe. And so I'm pulling this from a book called Show Me God. It's by Fred Heron, and he has a series of what he calls bottlenecks. I'll just call them challenges. And I'm going to summarize some of them, and some of them I might just read word for word because they're just they're just too well written, and why mess with it? So looking at the first one, and he starts out by talking about stars. And so bottleneck number one, he's talking about the star must not belong to a binary or multiple star system. In other words, there can only be one, like what we have in our universe. We've got the sun. It cannot have multiple stars. Okay, so right off the bat, this eliminates 2/3 of the stars in our universe. Right there. And again, we're looking for a planet that's going to be camped out close to a star, of course, like our sun, that can support life. And what he's saying is you can't have a solar system with a binary or multiple stars, more than one star in the solar system. That just messes everything up. And he goes on, the reason why is planets with circular orbits cannot form there. And furthermore, the star must be the right size. A star smaller than the sun would require a planet to orbit much closer, but if the planet orbits too close to a star, or a moon for that matter, it'll mess up the tidal forces, and when the tidal forces are messed up, the star rotation of the planet slows down. I know this is complicated, but you mess up the tidal forces, it causes the planet's rotation to slow down, and thus one side of the planet will end up cooking while the other side freezes. Okay. He goes on to say, a star that's any larger than our sun would have burned itself out long before any intelligent life would have evolved. Okay, so this Fred Heron, oh boy, forgive me, I'm probably mispronouncing his name, is assuming some kind of evolution as far as, outsiders, secular scientists would look at this and be thinking about life evolving. Well, if you're thinking about life, extraterrestrial life evolving somewhere else in the universe, I would contend billions of years is still not enough, because random changes in genetic codes do not produce new, complex information. You can reshuffle what's already there, you can reduce what's there, but you don't produce new, here's the key word, complex information. It doesn't happen. It doesn't happen. In fact, even when Richard Dawkins was questioned, can you give an example of new complex information that has been observed in science as evolution? And he asked them to turn the camera off because he had nothing. And when he finally got the camera back going, he gave this long, drawn-out, heeing and hawing kind of answer that never answered the question. He danced right around that one. It doesn't happen, okay? And so anyway, I would contend that even billions of years is not long enough. But anyway, for the sake of old earthers and for the sake of secular scientists, for those who believe in evolution, you look at this, and yeah, if the sun is bigger than our sun, it would have burned out long ago. Obviously, this would be a little bit much bigger. It wouldn't just be a little bigger than our sun. It would have to be a considerable amount bigger, but still. And so moving on, he goes on to say, even without the tidal effect problem, I mentioned that earlier, a star must fall in the range between 0.83 and 1.2 solar masses in order for an orbiting planet to avoid either a runaway greenhouse effect or, as on Venus, or a permanent ice age as on Mars. And moving on here, he talks about bottleneck number 2, and he talks about a star, the host star, the star that's going to have a planet that can support life nearby, would have to find its beginning in surrounded by a protoplanetary disk, and about half of single stars do. Okay, so that number we mentioned earlier, it just got cut in half again. About half of those stars do. Disk would have to be short-lived and small. Okay, planets that have medium or massive disks are doomed to spiral their way into their host stars. Don't ask me to explain the science behind that. But anyway, moving on to number 3, the solar system where this planet would live could not have any large planets with elliptical orbits. The reason why is if there's a large planet with an elliptical orbit, it will actually destroy the smaller planet. And number 4, and very similar to number 3, he talks about you do need, on the other hand, a large planet with a circular orbit. I should have explained elliptical. The elliptical orbit is more of like an oval, I guess, is the oversimplified version. It's kind of an oval-looking orbit, whereas you do need a large planet with a circular orbit. The reason being is a larger planet with a circular orbit will actually deflect most of the comets that are passing through your solar system. And you do not want a large comet to smack your planet. When that happens, no life. If there's life there, the life is dead. And so anyway, number 5, he talks about the Goldilocks zone. And the Goldilocks zone, okay. You guys remember the 3 bears and Goldilocks, and she's got the small bed, the big bed, and then the bed that's just right, and the porridge that's cold, too cold, and another one that's too hot, and then another one that's just right. Well, they're talking about the Goldilocks zone. The planet has to be in this zone that is not too hot and not too cold. Not only that, though, the planet has to have the right orbit around its host star. Otherwise, you're going to have problems depending on if it's too close to the star or too far away from the star. I mentioned that earlier a little bit. A former NASA astronomer, Michael Hart, says this: if the Earth's orbit were only 5% smaller than it actually is during the early stages of Earth's history, there would have been a runaway greenhouse effect, and temperatures would have gone up until the oceans boiled away entirely. On the other hand, though, he's found that if the Earth-Sun distance were as little as 1% larger, there would have been runaway glaciation on Earth about 2 billion years ago. I don't buy into an old Earth, sorry. But anyway, the Earth's oceans would have frozen over entirely and would have remained so ever since, with a mean global temperature of less than negative 50 Fahrenheit. Again, we're looking at factors or challenges for life existing on any planet. And as we continue to go through these, you see that the odds just keep getting more and more narrow. more and more difficult for there to be another planet out there that could even support life, let alone life evolving on it, which is a whole different matter that we're really not going to touch on in this series. But just the impossibility of there even being another planet out there that could support life. And so moving on to his example number 6, he talks about the planet's got to have the right force of gravity. The gravity cannot be too strong or it'll crush all of its inhabitants, right? We'll all just kind of squish the second we're born. Well, we wouldn't be born, but anyway. But not, okay, so not too strong, but yet it's got to be strong enough to hold in an atmosphere. And yeah, it has to be strong enough to hold water vapor, but at the same time, if it's too large, if the planet is too large, and by that, gravity is stronger, the larger the mass, the larger the planet. So if you had a larger planet, it would hold on to hydrogen, methane, and ammonia, and you'd have an environment similar to Jupiter. So again, more issues here. And Fred goes on to talk about the planet's size and temperature. There's a link between the size of a planet and its temperature. And he says that the planet has to have a mass of at least 0.85 of the Earth's mass, but no larger than 1.33 of the Earth's mass. Again, just more factors, more challenges for life. And moving on to his bottleneck number 7, he says that the planet that's supposed to be supporting life must be part of a double planet system. And, well, what he means by that, and what we see here on Earth, is we have this moon. And our moon is relatively large compared to most moons. And our moon, it's like an anchor, and it keeps us anchored in our spot so that it stabilizes the Earth and keeps the Earth from being attracted to Jupiter or any other large planets, causing the Earth to tilt on its axis and screw up, cause our climate to either go into a runaway greenhouse gas type environment or a permanent ice age. So again, you need to have that moon there. Now the moon comes back into this later, but again, you need that double planet system in order to keep the planet that is supporting life in check so that it doesn't have these attractions going on with other larger planets. And so moving on, the planet has to have some means of retaining its carbon dioxide. And this is interesting. Earth, this is how it works on Earth. Okay, water is constantly depleting our atmosphere of carbon dioxide. Okay, and what happens is parts of the surface of the Earth, different organic material, ends up getting flushed down to deeper depths in the crust of the Earth, right? And this is where it decomposes. And normally it would get stuck there, but because of the tectonic activity on our planet, the thickness of the crust of the planet, the crust is always moving around. We're having volcanic eruptions, we're having earthquakes, and that carbon dioxide is allowed to release. So again, it's interesting how all these cycles work. You have to have the right thickness of crust in order for that to take place. Again, you can't have life without it. And so moving on, and kind of on that same note, we have two different kinds of thicknesses of crusts. And this is oversimplifying it, but we have our granite rock, which is what most of the land mass on this planet is composed of, and it's lighter. It's lower density, which causes it to rise up above sea level. And then you have the heavy basalt rock that goes down, and that's, causes all the water to rush to one spot, aka the oceans, and keeps all the water in one spot. Without this system of differing crust, again, we'd have a planet that was just covered in water, which wouldn't work out very well for us. And so anyway, that's all I'm going to read from the Show Me God book. Tomorrow we're going to look at some other factors, and we're going to be looking at many of the different various factors within our universe that, again, seem to indicate a designer, a fine-tuner, a creator. And so with that, come out to the website, youthapologeticstraining.com, and there, guys, you can leave comments and questions. Also, you can catch me on Facebook, Google+, and Twitter. And with that, I love you guys, and I'll see you tomorrow.